Ladies and gentlemen, now for something completely different. Welcome to week 5 of our 7-week series called Deep Time, Global Change and You. And I have the distinct pleasure to share the stage with the first, but not the last, of our speakers who has his own Wikipedia entry. So Professor John Clague is the Canada Research Chair in Natural Hazards, of which you've seen one, at SFU, and he's been that chair since 2003. He's also the Shrum Science Chair, and he's held that chair since 1998, and that was also the year that he was elected to the Royal Society of Canada. And you have to sort of think of the Royal Society of Canada as the National Olympic team of scholarship, where everyone's just a bit older. He is a member of the Department of Earth Sciences. He's also an associate member of the Department of Archaeology, like Rolf Matthews last week. Before he came to SFU, he worked for 20 years for the Geological Survey of Canada. And before that, he got his PhD from UBC, and before that, his master's from Berkeley. And long time ago, he got his first degree from Occidental College in LA. Now, he's received many awards, and I'm not going to list them. I haven't done that for the other speakers. He has very diverse interests, centered now on natural hazards, but also the social aspects, not just the scientific aspects. He's trained as a geologist. He is an expert, for instance, among many other things, on the history of this area in the last 2 million years and how the latest, most recent glaciation created what we see around us, at least part. And more generally, just on the geology of the last about 2 million years. In this region, and the geology and the history that you see in the geology has been seen a lot of dramatic change. And his talk tonight will touch on some of that dramatic change, and the title is Magnitude 9, How We Learned That the Largest Earthquakes on Earth Happened on Our Coast. Please join me in welcoming Professor John Clague, FRSC.
Thank you very much, Arn, and it's a real pleasure to be here, and I thank you all for coming. I hope everybody can hear me back there. This is a passion of mine. I've kind of pursued this since the time that I worked for the GSC and continued as a research interest at SFU. Of course, it has a practical side to it as well, because we're trying to really understand the risk we face from earthquakes. And my pitch tonight is going to be that about 30 years ago, we thought we really understood earthquakes. And then sort of geologists and geophysicists came along and shook things up a bit and said, well, you don't really understand it, because we do get these, I call them world-class earthquakes. I obviously kind of have this bipolar attitude towards earthquakes. I like them, but I hope they don't occur. But we do get magnitude 9 earthquakes off our coast. And the reason that this was not appreciated in the past, of course, is that we haven't had one historically. There are First Nations accounts up and down the coast, all the way from British Columbia down to California, of these earthquakes, but we haven't a record of them, kind of a Eurocentric based record. So we have to turn to other lines of evidence, and it's kind of this story that I want to develop for you tonight. I'm going to go back a ways. I'm going to go back about 50 years to kind of set the stage for how we came to know that we get these earthquakes. And it was an exciting time for me 50 years ago, because that was when the plate tectonic paradigm got established. It is probably the most important sort of new paradigm that's developed in at least earth science in the past 2 centuries. And it's really radically changed the way that we view the world as geologists and geophysicists, and has allowed us to really better understand these huge earthquakes. So I think we can do better than these animals here in terms of forecasting where the next and when the next earthquake is going to be, but some people would argue otherwise, I suppose. So let me start here. Before I get into the subject, I'd like to just make sure you understand what an earthquake is and sort of where earthquakes occur in Canada and BC. So an earthquake is a product of the slippage of blocks of the earth crust along a fault. You don't get an earthquake unless you actually have a sudden displacement of crustal rocks along what we call a fault or a discontinuity or a breakage plane in the Earth's crust. And the size of an earthquake depends a lot on the area of the fault that ruptures. So if you rupture a very large area of a fault, you're going to get a larger magnitude earthquake than you would if you just rupture a smaller area. It also depends on the amount of displacement you get. So if, say, those two blocks of the crust slip 30 meters over a large area, you're going to get a very large earthquake. If they slip less than a meter, you're going to get a smaller one. Generally speaking, that's the way it works. And we refer to the location where that rupture first occurs as the source or the hypocenter of an earthquake. The epicenter is a position on the Earth's surface directly above the source where the fault initially ruptures. Just a little terminology, just want to make sure you understand earthquakes. So this is a map showing epicenters of earthquakes. It's a little dated now, but the pattern hasn't really changed. The size of the earthquake is shown by the diameter of the circle. And of course, the first thing you notice is earthquakes aren't random in Canada. One thing you really notice is that, of course, we have a lot of earthquakes on the West Coast. No surprise there. But even on the coast, they're not randomly distributed. We get this zone kind of coming down near the U.S.-Canada border, a little north of that. And the epicenters of earthquakes shift inland. Whereas to the north, from northern Vancouver Island up past Haida Gwaii, there's a very clear linear trend of earthquakes. And this pattern was well recognized long before we recognized that these giant earthquakes occur. And it's important to remember that none of these are giant earthquakes. These are all moderate to large earthquakes. The largest one here would be an earthquake on Haida Gwaii that had a magnitude of 8.1 in 1949. But most of them are smaller. Just as a sidebar comment, you can see that there's also an area in southern Ontario and southern Quebec where you have a lot of earthquakes. They don't tend to be as large as the earthquakes on the West Coast, the largest earthquakes on the West Coast, but they are extremely dangerous because of the infrastructure that you have in cities like Montreal, Ottawa, a lot of masonry buildings. They don't have the provisions in they have the provisions in the building code, but the buildings would not be able to withstand the same size earthquake that buildings in our earthquake belt would. So, you know, I wouldn't be surprised if sometime in the future there's a magnitude 5 or 6 earthquake that causes a lot of damage to a city in southern Ontario or southern Quebec. However, most of the energy release from earthquakes occurs in British Columbia, right up to the Alaska border and in Yukon Territory. So this is the area we're going to focus on, and I'm just going to show you a little bit closer. Same pattern, a little bit blown up, and some of the large earthquakes that have occurred historically. Doesn't show the big Haida Gwaii earthquake, the magnitude 7.7 earthquake. It's a bit of a dated slide. There was a big earthquake, I'm sure you're aware, up there. One of the largest that's occurred in Canada in its history. However, of course, this part of the coast is sparsely populated. Most of the earthquakes are offshore. It's not till you get down into this territory that you begin to go, oh my goodness, maybe we have a problem, Houston. There's been a big earthquake in 1872, very close to the BC-Washington border. Quite well-known earthquake, the 1946 Central Vancouver Island earthquake was a magnitude 7.3. And just to put that in perspective, the earthquake that devastated Christchurch was a much, much smaller earthquake than that. It was a magnitude 6.3 earthquake, released 30 times less energy than this magnitude 7.3 earthquake. So the areas that we're really concerned about in terms of historic earthquakes are central Vancouver Island, southern Vancouver Island, the Victoria area, and Vancouver and the Puget Lowland area to the south. It's areas of historically high seismicity. And as I said, this was the picture that we had really 30 years ago. And at that time, we had seismic provisions in our building codes, and engineers and architects were designing public buildings, large buildings, to withstand the ground motions from earthquakes like that, historic earthquakes. And this just shows kind of the damage pattern from two of those particular earthquakes. I mentioned the 1946 Vancouver Island earthquake, magnitude 7.3. Centered, the epicenter was near Buttle Lake on Vancouver Island. Interestingly, caused the Lionsgate Bridge to sway. I talked to an old timer many, many years ago who happened to live in Richmond, and he was outdoors at the time, it was early in the morning, and he described the earthquake waves coming through like waves at sea. So the surface of the delta was kind of behaving like you would expect an ocean to behave. A little bit of damage in Victoria. As far as I know, no damage in Vancouver, almost no damage, but it certainly was strongly felt in these two cities, a couple hundred kilometers away from the epicenter. So that's what a magnitude 7.3 earthquake will do in terms of the area of damage and the area in which it's felt. And then back in 2001, I don't know how many of you were here, I was at my desk at SFU and a train backed into the building. That's what it felt like. An earthquake between Seattle and Olympia, Washington occurred. It was a deep earthquake, caused a couple $2 billion damage in Seattle and Olympia, and was strongly felt in Vancouver. I was just talking to somebody yesterday who was in a high-rise building in downtown, and he pretty freaked out, because you get this oscillatory swaying of buildings, and the upper floors can move considerably during an earthquake like that. But engineers design these buildings to do that, so he had nothing to worry about. Easy for me to say. Okay, so now I'm going to get on to the thrust of my presentation. So as I said, we've known for a long time that we get earthquakes here. People of European descent have experienced these. In fact, the oldest archived earthquake that I can find is one in 1783. There were some Spanish explorers who overwintered on Vancouver Island, and they were bemoaning the winter on Vancouver Island, on Nootka Island, but they also said it was exacerbated by the fact they had a damaging strong earthquake. So that was 1783. And since then, we've had, of course, many other earthquakes, but they've all been, the big ones have not exceeded about magnitude 7.5. Only 25 years ago, and that's not too long ago, do we realize that we get rarer but much, much, much larger earthquakes. Magnitude 9 earthquakes. Good comparable example would be the Tohoku earthquake, the Japanese earthquake that occurred a little over 2 years ago, magnitude 9 earthquake that produced that horrific tsunami that killed about 20,000 people. We get those earthquakes, and I'm going to kind of show you how we come to know that. So that's the thrust of my presentation, and it's a commentary on science, how science progresses. So there's a kind of a parallel story that goes on here that I'll comment about, is that, how does science work? And this applies in all fields of science. This is a story about earth science, but it would apply in any field of scientific endeavor, that we build upon the knowledge that our predecessors provide. So I'm going to take you back to the early 1970s. That's not Earl Flynn. The guy looks like Earl Flynn to me. His name is Henry Hess, and he was a captain in the U.S. Navy during World War II. And when he was not busy evading sort of Japanese planes, he was also surveying the ocean floor as a Navy commander. He was determining the bathymetry of the ocean floor. And he was a very clever man. I think he had some oceanographic training. And he noticed that there were elevated parts of the ocean floor, these mid-oceanic ridges. And he was aware from what others had done that these were volcanically active areas. There were volcanoes on the ocean floor along these ridges. And the ridges decreased and the water depths increased away from the ridges. So he proposed, and it wasn't built entirely out of the blue on his own ideas. There had been predecessors, earlier work done, kind of which he built upon, that these volcanically active ocean ridges were places where oceanic crust was created and moved away from the ridges. And this was a pretty wild idea at the time. And he published this in a paper titled History of the Ocean Basins in 1962. It was a Geological Society of America volume in which this paper appeared. And so he didn't really have any solid evidence for this. And then really, what really started things going, what really started the sort of plate tectonic revolution, if you will, came a year later. And it was Harry Hess's idea that kind of stimulated these guys, Drummond Matthews and his PhD student, Frederick Vine, to test this idea that new crust was being created and moving away from these mid-ocean ridges. And these guys had a novel idea. They recognized that the Earth's magnetic field periodically switches. It goes from north pointing to south pointing. And don't ask, I'm not an authority on why that happens, but in Earth history, the magnetic field, not the rotational field, but the magnetic field undergoes a 180-degree switch. And this had been previously documented. And so these guys said, well, if that's the case, we can look at the polarity of basaltic rocks on the ocean floors. The ocean floors are largely basalts, and they record the Earth's magnetic field when they cool and crystallize. And so they had this idea, they could test Hess's theory by determining the magnetic polarity of basalts on the ocean floor. And they did this by basically dragging magnetometers, instruments that measure the magnetic field, across the oceans and sort of figuring out what the polarities of the ocean floors basalts were in different places. So this is kind of how it works. You all are aware the Earth has a magnetic field. We're presently have a north pole there and a south pole there in terms of magnetism. Every once in a while, the field undergoes a 180-degree shift, probably over a period of about 5,000 or 10,000 years. Not too sure. It's related to convection in Earth's mantle and probably something to do with the core. And we know from studies done on land that we can actually age date these volcanic rocks and determine their polarity. So basically this diagram shows a binary plot of when the Earth's magnetic field was normal as it is today, and in white when it was reversed. So you can see for the past 800,000 years, it's a million years, the Earth's magnetic field has been normal. About 786,000 years ago, it changed to normal from reversed. And you've got a kind of a barcode back in time. This goes back 5 million years, but they've extended this back hundreds of millions of years now. This is a land-based record. It's based on measuring the polarity of the basalts as they crystallize and cool, the little grains of magnetite, the little magnets in the molten rock align themselves like fish in the water pointing to the North or the South Pole. And it's really easy to measure that. These rocks tend to be very strongly magnetized. So you've got this land-based record with these dated rocks of normal, reverse, normal polarity. And that's what Matthews and Vine were working with. They said, well, you know, if Hess is right, we should see those reversals in the basalts on the ocean floor as they move away. As new basalt is created, it's going to align itself with the field that prevails at the time. And eventually the basalts are going to move away. You're going to get new basalts, and maybe it's in this period when the field is reversed. And wow, what they found was amazing. They found these bands of normal and reverse polarity, perfectly symmetrical about the ridges. And so what this told us right away is with these alternating normal, reverse, the same on both sides of the ridges, that you have to have the seafloor spreading away from these ridges and kind of recording like a tape recorder these fields of normal and reverse polarity. It was a very amazing finding. No one would have ever thought of that. It instantly told Earth scientists that the seafloor, you're getting spreading away from the ridge, you're getting new crustal material forming at these ridges, and it's moving away slowly at rates that you can determine because you know the age of each of those bands of normal and reverse polarity. And this is just a plot off our coast of the spreading ridge. It's called the Juan de Fuca Ridge. If you go there today, you'll see active volcanism on the ocean floor where new basalt is being created. It cools below what we call a Curie point, and it's normal. If you go back away from the ridge, you hit that first band of reverse polarity, which is about 780,000 years. And you can work your way back there millions of years, basically recording the spreading and creation and spreading of crust at these mid-ocean ridges. So we have mid-ocean ridges in the Pacific Ocean, we have them in the Atlantic Ocean. Iceland actually sits on one of these ridges, the Mid-Atlantic Ridge. It's one where you actually have a landmass sitting right on top of the spreading center. So part of Iceland is going to the west and part of it's going to the east, and it probably explains why they're such strange people, but I'm not sure of that. Anyway, so what does all this have to do with earthquakes? Well, first of all, you know that really material is being created and it's moving towards the coast of British Columbia, Washington, Oregon, and California. Now, if you think about this on a global basis, there has to be something that's consuming crust. I mean, otherwise the planet would just be expanding like a balloon. You know, you can't create new crust at the ridges without consuming it somewhere if you're going to maintain an Earth of the same size through geologic time. And we know that the Earth has not changed fundamentally in its overall diameter or circumference in geologic time. So what do you know right away? Somewhere that new crustal material is being consumed, and it's being consumed at what we call subduction zones. There's a big subduction zone off our coast that extends from central Vancouver Island down to Northern California, where that basaltic material, the slab of basalt that's kilometers thick, is going down beneath North America. We are in an environment where one plate is moving down and being consumed beneath another. So very soon after this paper was published, people began to think in terms of what does this mean in terms of earthquakes? Because where you have two plates that are colliding with one another, that's where you might expect earthquakes. And in fact, that setup at a subduction zone is where we get the biggest earthquakes on Earth. And we have one on our coast. And it's right here. It's a small plate. It's called the Juan de Fuca plate. It forms at the ridge, the Explorer Ridge, Juan de Fuca Ridge, and it moves to the northeast and basically is consumed as it moves down into the mantle beneath our feet. So I think at about, I want to say about 60 kilometers below us here, that plate is in contact with the bottom of North America. And that's a recipe for earthquakes, big earthquakes. On Earth, there's about 7 large plates, including the North America plate, this plate here, the Eurasian plate, very large plate, forms Europe and much of Asia, the African plate, the South American plate, the Antarctic plate, and then there's a bunch of smaller plates as well. Some microplates, some larger. In some places, such as the Southwest Pacific, it gets really complicated. You've got a lot of microplates, you've got subduction zones all over the place. It's no wonder, Japan and Indonesia have so many earthquakes, not to mention volcanoes, because an ancillary complementary element of subduction is that as crustal material goes down into the mantle, it heats up and you get volatiles coming off which melt continental crust and produce the magmas or the molten materials that form volcanoes. So back in the 70s, this picture had evolved to the point where people recognized, pretty well conceded, if you will, because there was a lot of resistance to the plate tectonic theory. They conceded that there was subduction occurring off our coast, that crustal material, oceanic material was moving down beneath North America, and we lived in a subduction zone environment. This is one of the 3 types of plate boundaries. Very famous Canadian geophysicist by the name of J. Tuzo Wilson recognized that not only are there spreading centers where new crust is created and moves away from a center and subduction zones, but there's a 3rd type where plates slide past one another horizontally. And that's the setup for the San Andreas Fault in California, and it's a setup for the Queen Charlotte Fault off Haida Gwaii. And so J. Tuzo Wilson is probably our most famous geophysicist, major contribution to this plate tectonic revolution at the time. So going back to this time when plate tectonics was the new paradigm, people recognized then that this was the northern end of a subduction zone. There's a fault there that extends across Vancouver Island where we get this break in the pattern of earthquakes. And basically to the north, you have one of these transform faults where the 2 plates, the Pacific plate and the North America plate, are sliding past one another. And to the south, you have a subduction zone. Now, the earthquakes that occur inboard of the subducting plate are not these magnitude 9 earthquakes. These are either earthquakes in the crust, they're shallow earthquakes, or they're earthquakes in the subducting plate, which we call the Juan de Fuca plate. And so scientists began to say, well, there are no big earthquakes. We had never experienced one historically. What that probably means is that the 2 plates are sliding frictionlessly past one another. That was the thinking, and that we could not experience a magnitude 9 earthquake. This really ran counter to the fact that all other subduction zones on Earth produce magnitude 9 earthquakes, but nonetheless, I remember back in the 70s and early 80s, there was this big argument, and the prevailing thought was that you've got this continuous motion at a rate of about 5 centimeters per year, so that much per year. The 2 plates are sliding without friction, without being locked against one another. And people were happy. They said, oh, no magnitude 9 earthquakes, good deal. So that was the question. But there were other scientists who were saying, well, gosh, why should this subduction zone be different from any other subduction zone? Why? No other subduction zone shows this continuous motion of plates. Rather, they show what we call stick-slip behavior, where one plate gets hung up against another. Basically, the subducting plate is hot, is buoyant, tends to hang up against the bottom of the overlying continental plate, and strain accumulates. The offshore plate wants to move down beneath the continent, but it can't. It's hung up. And ultimately, of course, rocks can only hold so much strain, and ultimately you get a rupture, and that strain is released. Whatever is accumulated since the previous earthquake is released in one of these big earthquakes. This is a setup for the biggest earthquakes on Earth, or subduction zones where you have a fault that might be 1,000 kilometers long that slips with movement between the two plates of up to 20 or 30 meters within a minute or two. And that releases an unbelievable amount of energy, like happened in Japan, for example. So this guy, I know him, he's still alive, George Plafker, he's one of the best geologists in the world. Great guy. He studied subduction zone earthquakes in Chile and in Alaska. In 1964, there was the second largest earthquake historically on Earth, magnitude, I think 9.2. And what he documented was the deformation of the ground surface that occurred during that earthquake. Remarkable. Now remember that you're storing up all this energy and you release it suddenly during this earthquake. What happens? Well, he mapped out the area that the land dropped. So there was a instantaneous lowering of the land surface over an area of several tens of thousands of kilometers, up to 2 meters. The land just dropped. There's pictures from this area of subsidence near Anchorage of little homes sort of sitting, coastal properties sitting 2 meters below sea level. And if you happen to live on Montague Island and experience this earthquake, and I don't know that anyone did, within a minute, the land would have risen up to 9 meters. So you'd be standing at the shoreline, and a minute later, you'd be 9 meters way above the top. That would have been exciting. I would have loved to have been there. Great. But the key is he kind of recognized that this is not a random pattern. You get this zone of subsidence, and then outboard of it, you get this zone of uplift. So what does that tell you about what's happening in the earthquake? I think I'm going to move on. What it tells you is what you would expect. If you think about a subducting plate, this is a cartoon, where one plate is hung up against the other. Think of the edge of a carpet. It's getting rumpled because it's not slipping against the underlying surface. You get squeezing. You get compression slowly over a period of perhaps hundreds of years. The edge of the plate gets compressed, it gets elevated, and you've got this elastic storage of a huge amount of energy. And then during the earthquake, once that fault ruptures, once the fault can no longer basically store strain, and you get a rupture, then it's like a release of a spring. The plate extends outward, you get uplift on the rising limb of the fault, and you get subsidence behind it. That's the very pattern that Plafker documented during earthquakes. If I can just return back to that slide. The exact pattern you'd expect. So this is the zone of subsidence where the plates extend and drop, and then on the rising limb of the fault's actually rising out towards the ocean floor, you get this area of uplift. Okay, we're getting closer to modern times. This is when this was the stage at which we recognized that these huge earthquakes occur. 1987, sort of Brian Atwater, he's got to be the closest thing to a human backhoe I've ever seen, because the guy can dig more dirt than anyone on Earth, was working in tidal marshes along the Pacific coast. And he was aware of Plafker's work. He was aware of the expectation that you get this inboard zone of what we call coseismic subsidence, where the land drops. And again, it was kind of an aha moment. He said, well, if the land drops, where would you record? Where would you get a geologic record of an event like that? And the best place is in tidal marshes. Say you go out to Lulu Island, the tidal marsh, and if that happened to be in an area where the land were to drop a meter or two, it would be inundated by the sea. The marsh would drop down in the tidal zone the plants would be covered by water, and eventually they'd be buried in tidal muds. So his working hypothesis was if you get one of these big earthquakes in a marsh, which is graded out to, say, mean sea level, you should see this sudden land level change. You should see a buried marsh surface overlain by tidal muds that normally are deposited at lower, deeper, lower in the tidal zone. It's a couplet that kind of you would expect in an earthquake. You can't base a great earthquake on a single record like this, but this in fact is a tidal marsh surface, a peat layer that existed in AD 1700 that was dropped down 2 meters and covered by tidal muds. So Brian, when he found the first of these in the Nyawyakam River estuary in Washington, then proceeded to go up and down the coast looking for similar evidence to try and build a story around a spatial pattern of this subsidence. This is a cartoon that kind of shows what happens. Before an earthquake, you get a tidal marsh backed by maybe a coastal forest, a Sitka spruce forest, hemlock. During the earthquake, the land drops, it subsides in this zone behind the area where the land rises. The marsh is now no longer really in equilibrium with water levels. It gets covered by tidal waters. Ignore this, a tsunami comes in, talk about this in a moment. But after that, you get accumulation of tidal muds on top of it. So you sort of expect a couplet like that, peat, mud, very sharp contact. And in fact, in many of these exposures, you can see the rooted in-growth position marsh plants with leaves that are draped over and buried by the tidal muds, indicating that it was a very sudden burial event. And this is an interesting story too. If you go out into some of these tidal marshes in Washington, you can see these trees, these dead standing trees. This is called the ghost forest of the Copalis River. And people didn't really understand what in the heck trees were doing in a tidal marsh. You know, this is basically a high marsh environment, and this is not the place that trees really like to grow. But they had no explanation for this. Well, it turned out that, first of all, you might expect that these trees are rooted on that surface. Well, they're not rooted on that surface. They're rooted 2 meters below that surface. And they're associated with the AD 1700 forest, which was 2 meters higher. During the earthquake, these trees were dropped into the tidal zone and then covered by tidal muds. So you get a situation like this, where you get tidal marsh, the roots of a big Sitka spruce in growth position, buried by tidal muds. You know, and I think it's kind of interesting because anyone in their right mind, unless they actually began to dig in here, would just assume that that's a tree that's rooted on the surface, but it's not. It's way below the surface and totally related to an earthquake that occurred 315 years ago. So in some marsh environments, particularly in Washington, you get a series of these couplets, these peat mud couplets, each of which we now know is a product of an earthquake. You can think of this as being a bit of a barcode. You get this same pattern of soils, silts, soil, silt, soil, silt, all through the coastal area of British Columbia, Western British Columbia, Vancouver Island, Washington, Oregon, California. And in fact, it's more than just similar. You get weak soils, which probably record shorter intervals between earthquakes, and very strong soils where the marsh gets fully developed and likely spans hundreds of years. So you see not only a barcode pattern, but you see similar soil developments if you count down through this sequence. And it's very strong evidence when you find this record over distances of hundreds of kilometers that you're dealing with the product, the geological traces of these huge earthquakes. And this is a story that Brian developed for the coastal wetlands in Washington. Just so you have a sense, this is a time scale here from 4,000 years ago up to the present. These are the range in radiocarbon ages for events that represent earthquakes. There's a range there because carbon dating is imprecise. We can't be super precise. There's often uncertainties of tens of years, in some cases a lot more. And this pattern here just represents a sequence of marsh formation, earthquake, wham, goes down. New marsh forms, wham, the earthquake drops it again hundreds of years later. You can see the tape unfolding through time. And this particular record on land records 7 events over the past 3,500 years. And we find this same story up and down the coast. We know that the average recurrence for these magnitude 9 earthquakes is 500 to 600 years. We now have a record from the deep sea that goes back 10,000 years, and we have a record of 20 events. It basically is the same recurrence, 20 events in 10,000 years, 500-year recurrence interval. Now, geologists were able to date this most recent event using these trees that were killed by the earthquake to within about 20 years, sometime between AD 1690 and AD 1710. They were using tree rings and carbon dates, and some very clever Japanese scientists said, well, let's see, 1700. Oh, we have records of that. Oh, these earthquakes trigger monster tsunamis. Maybe that tsunami hit Japan. And when they looked for it in the record, they found it. It was called the orphan tsunami. It was a tsunami that was not accompanied by ground shaking. It totally freaked the Japanese out. I mean, they know when an earthquake occurs, it's a possibility they're going to have a tsunami. This one appeared out of the blue, ran up 6 meters along the coast of Honshu. You can imagine how big it was on our coast because we were the source of it, Basically, North America produced that tsunami on January 27th, 1700 in Japan, which means the evening of January 26th on our coast at 9 p.m. I like that story because geologists had spent tens of thousands of dollars radiocarbon dating stuff, telling us that it was 1690 to 1710. The Japanese tell us when it occurred to the nearest hour. What a story. So I'm getting close to the end here. I know I have to finish up, but I just want to add the contribution that the very important contribution geophysicists made. Because you could say, well, you really can't say that the one in 1700 was the last one. We've had 20 in 10,000 years. We're certainly going to have one in the future. And if you look at the average recurrence, 500 years, well, we're getting a little closer to the next one because it's been 314 years since the last one. That doesn't mean it's imminent, but we're getting closer, let's put it that way. So the geophysicists have used this amazing technology. Part of this story is technology. With satellite global positioning systems and precise locations on the ground, you can locate a point on the ground to within millimeters. Actually millimeters, think of that. How precise that has to be from space to locate something on the ground to millimeters. And we've had that capability for close to 30 years now, I guess. And so our geophysicists based in the Geological Survey in Sydney have stations that they monitor continuously. There's one in Victoria, there's one in Penticton, there's a number of them around. And what they're able to show is that Victoria is getting closer to Vancouver. It's moving closer to Vancouver. It's not going to solve our ferry problem, but it's getting a little closer to Vancouver. And Vancouver Island is going up. We used to thought that was due to tectonics, but what it really is due to is this squeezing of North America by the downgoing plate, with the downgoing plate hung up against the bottom of the edge of North America. Graphic proof that strain is accumulating for the next earthquake. And it's remarkable to me that you can actually make measurements like that to within millimeters, because the actual rates of shortening between Vancouver and Victoria are of that order. They're millimeters per year. So just remarkable technology. And from that pattern, knowing how the ground is deforming, you can project downward and determine what's happening at depth. And so these guys, Roy Heinemann and Kellen Wang, two of the best geophysicists in the world, they work for the Geological Survey of Canada, have mapped out where those two plates are hung up. Think of that as a projection into the surface of this downgoing fault. So we have what we call a locked plate boundary that extends offshore to where the plate goes down beneath the ocean floor to probably somewhere close to or inland of the present shoreline. So that's where this strain is accumulating that's ultimately going to be released in a giant earthquake. So I'm going to close with the more recent developments and where we hope to go from here. Secondary effects. These, when you hear about big tsunamis, commonly they're produced by these type of earthquakes. And the reason, of course, is that when the fault slips, the edge of the continent rides up onto the seafloor, and you get this displacement of the water column over an area of tens of thousands of kilometers. That produces huge tsunamis, not little picayune things, the really big ones that move away from the fault towards across oceans with little loss of energy and impact shorelines. So in our case, we're close enough to the edge of the continent here that after an earthquake, we would have tsunamis arriving in about 15 to 25 minutes in coastal communities. Big concern. Less of a concern for Victoria and Vancouver because they're much farther inland and they're protected a bit by Vancouver Island. And we all know about tsunamis. We kind of learned about tsunamis during the Sumatran earthquake in the Indian Ocean. We learned more about them from the Japan earthquake. I'm not going to talk about them, but they are very, very, very different than storm-driven waves. People go to Tofino to watch the waves in the winter. This is a totally different phenomenon. And we find that evidence too. So not only do we find the evidence of land level change, but we find the deposits of these tsunamis that run up along our shoreline. So this is a layer of sand deposited during the 1700 earthquake inland from Tofino. I like to show this one to Tofino audiences. And then finally, I want to talk about recurrence. So we know from the offshore record that we get these earthquakes on average every 500 years or so. We have 20 of them, and we can play a little game with the dating. I'm going to skip that one. Here's the last 20, starting in 10,000 years ago, the last one in AD 1700. This is thought to be roughly a measure of the size of the earthquake. They do differ in size. But the key thing is to notice that they're not uniformly spaced along that timeline. You get some that look to be clustered, and you get intervals between successive ones that sometimes can be 1,000 years. And so Mother Nature is not delivering these things religiously every 500 years. And it depends upon how you want to do the statistics. They say statistics lie, but nonetheless, statistical analysis of this data set indicates this is not a stochastic data set. It's not a random data set. These things are occurring in clusters. So a big question is, are we in a cluster or are we in an interval between two clusters? It makes a big difference. There's a big cluster of earthquakes here, and the most recent ones are kind of clustered. So where will the next one be? Will there be 1,000 years after 1700 AD, or is it going to be 100 years, or 200, or 300? Unfortunately, that makes a big difference in terms of calculating the probabilities, the conditional probabilities of the next earthquake. So that's something we want to better understand, is what is driving the non-randomness, the clustering of earthquakes at this subduction zone. So I'm just going to close with one last slide. What do we want to do in the future? Well, we want to actually be sure we've got a precise map of what portion of the fault at depth is actually locked. Because if we're wrong and the lock zone extends farther to the east beneath, say, Vancouver, then we're going to experience a stronger ground shaking than we would otherwise. So we need to be darn sure exactly what is the spatial pattern of that locked interface. So that's an area of research. And then we're trying desperately to improve our chronology. Fortunately, we have to rely on radiocarbon dating for old events, but we can be a little more clever in what we date to get reduced uncertainties on the ages of past earthquakes. And that helps in terms of evaluating this randomness versus non-randomness issue. And then I've kind of talked about, almost implying, maybe I've said explicitly, that the entire subduction zone ruptures. And that is the current model, that most of these earthquakes rupture the entire fault from Northern California to central Vancouver Island. That strikes me as being odd, because almost no other subduction zones operate that way. They're what we call segmented. A portion of the plate boundary fault ruptures, and maybe a year later, 50 years later, another section ruptures. To get this pattern persistently back 10,000 years strikes me as being unlikely. So I'm a skeptic on that one, but that's the current thinking, is that the whole subduction zone. What difference does it make? A partial rupture would generate a magnitude 8 earthquake, and a full rupture would generate a magnitude 9 earthquake. And the difference in energy release between an 8 and a 9 is about 30 times. So it's not just a linear scale, that's a logarithmic scale, much, much bigger earthquake. And then, of course, we would like to know if there are any precursor signals. Is in the lead up to one of these earthquakes, is there something that changes? You know, there's something in the deformation pattern, aside from strange animal behavior. My dog always reacts strangely. No. We would like, ideally, to be able to come up with better, something that tells us that we're getting close to the next earthquake, and we have yet to find that. But there are efforts being made to kind of look for what are called precursor signals that signal that an earthquake is imminent. And then, of course, I haven't talked about, this is more of a historical story, but I haven't talked about the impacts of these earthquakes on our infrastructure. We can get some idea of their impacts from the geological traces they leave. You know, we can identify things like liquefaction, we can identify landslides, we can estimate the amount of land level change. These gives us clues as to what will happen to our infrastructure. But we're in a position where I think we can come up with better estimates of the types and extent of damage when this next earthquake does occur. And I think that's it. My students call me Dr. Doom. So.
Professor, that was a masterclass in earthquakes. And the floor is, of course, open for questions and comments. And as per usual, I'll try to repeat back your questions so that everybody can hear, if that works. So we'll start here, and then we'll go there, and move on to the next.
My question is, I'm wondering, how well is the Canadian Building Code kept up on seismic design with the knowledge that the earthquakes are going to be greater here on the West Coast? Has the design of the buildings kept up with the seismic events that we might expect? And there's a second question is, with the Georgia Basin, there's recent discussion about that it could liquefy and the energy could go through much quicker, creating even a bigger earthquake than what was originally envisioned.
Right.
So there were two questions. One is, how have the building codes kept up with this new information, and what happens if the Georgia Basin liquefies, and what does that even mean?
Well, I don't think it's liquefied. It's more kind of how it would impact the waves moving through it. I'm not sure Well, I'll try the first question. There may be somebody in the audience who probably can answer that. In fact, the author of that paper. But in terms of keeping up with the building code, yes, there's a new iteration of the building code, and these great earthquakes are factored in. I haven't talked about this, but it actually the greatest risk from an infrastructural damage point of view is not from these earthquakes. It's because they're so rare. The greatest risk is from a more frequent, smaller earthquake of, say, magnitude 6 to 7.5. They're just more frequent. They have a smaller footprint, so it really depends upon where the earthquake occurs. But they're so frequent, they're 25 to almost 50 times more frequent, those 6 and 7s, than the magnitude 9, that they actually control the risk. So yes, they are factored into the building codes, but it's really the very strong short wavelengths, very spiky, high acceleration local earthquakes that really are going to be responsible for the most damage to, say, Vancouver or Victoria. Not to deny that the great ones won't cause damage too, but they're just rare. So there's this kind of trade-off between frequency and magnitude that comes into play when you're evaluating risk. And the kind of the effects of the basin, that's important. It's usually considered in terms of earthquakes that are generated locally. So if you have a seismic source in one of these basins, you can get amplification that results in higher ground motions than would otherwise be the case. So that's kind of the deep geology beneath our cities. We have a number of sedimentary basins that are capable of causing higher ground motions at the surface than would otherwise be the case. That has not been factored in. That's a recent finding, and it remains to be seen how that will be factored into the building codes.
Thank you. Yes, here, and then back there.
Thinking globally, is there any evidence of clustering of large earthquakes in one part of the world being related to large earthquakes in other parts? May help with your timing.
So the question is there some correlation between earthquakes in one part of the world, temporal correlation between earthquakes in one part of the world and earthquakes in another part of the world, if I get that right?
Yeah. Not that I know of, but it's possible I've missed studies of that sort, but not that we're aware of. There are
theory that would support that?
Pardon?
Is there any theory that would support that? Is there any reason why we might expect some correlation?
More on a regional scale. Like a big earthquake on our subduction zone is unlikely to have an impact on another subduction zone. But I know in Japan they're looking at sort of relationships between earthquakes, clustering. The Kobe earthquake in 1995, there's been a paper published that suggests it was related to a subduction zone earthquake on the Nankai Trough in 1946. And I'm not quite sure what the linkage is, but there's a larger probability that displacements along fault in a region can set up strains in adjacent areas that can lead to earthquakes. That for sure is possible. But on a global scale, I don't know of any relationship.
Okay, so there's one here, yep, and then at the back there after, yeah.
I thought there was an Atwater paper in the late 90s where he looked at accelerated ground subsidence in Japan as a precursor signal to earthquakes. Is that something that we can measure, or has it been sort of debunked? What's the status on that?
So the question is, the question concerns a precursor and some evidence from Japan about a potential precursor to a large earthquake.
Do you mean immediately before an earthquake, or I'm not quite sure I understand your question, Jared.
Yeah, within a short period.
Oh, no, Atwater's never published anything like that. There have been some other people that have suggested that from the micropaleontological evidence that you can get, and this is kind of evidence that the land slowly is shifting before an earthquake. It's quite controversial. Nobody, well, I'm skeptical that they actually are recording land level change over those very short intervals in a sedimentary sequence. I can talk to you about that later, but there's this whole issue of infaunal kind of activity by foraminifera that kind of lead one to believe that that kind of might not work.
Just as a follow-up, so there's two questions, one at the back and then there's one down here. But where are people looking for these sorts of precursors? What possible precursors could there be? Just to broaden that question a bit.
It's related to Jared's question. You can study these sedimentary sequences and you can look at sediments very close to the contact where that land drops, and you can look for evidence that the land is shifting. You got to discriminate it from sea level change, but that there's a change in the rate of land level movement. It's detected using elevation sensitive microfossils, mainly foraminifera. I don't know that there's really any really good studies done of other types of precursors. Now, when you deal with smaller earthquakes, people have looked at things like well water, the radon content of well water. The Chinese were really big on odd animal behavior. You know, things like snakes coming out of the ground immediately before an earthquake, or birds taking flight. And it's probably true that animals, in some cases, do detect something that's imminent in an earthquake, because some of those accounts are pretty well documented. On the other hand, most earthquakes, animals don't do anything strange. The earthquake occurs, and that's it.
We had a question here at the back. Yeah, there's a third one there. But
Yeah,
yeah.
hi. In a city like Vancouver, which is sitting on a subduction zone or near the subduction zone, Cascadia, how should we prepare ourselves for example, I'm thinking of our interface with industry, and specifically, although there are many industries operating safely within Vancouver, but
Yeah.
how should we be thinking, for example, should there be one of the largest chlorine factories in North America sitting on the mudflats on Burrard Inlet?
Right.
And we do not grandfather the building code, but there is also a train leaving from there almost daily that has 2,500 liquid tons of chlorine gas under pressure.
Yeah.
Meandering its way through our downtown and our neighborhoods. Should the public allow that? Even though the industry is operating safely at most
Right.
times,
Right.
that could be devastating.
Yeah,
both for fire, because as you know, it uses high voltage electricity
Yeah.
within those membranes to produce chlorine gas on one side, hydrogen gas on the other side, and has electrical tower on site. Should the public be more aware of those kind of situations, and what could happen in an area where they are increasing population?
So the general question is,
Yeah.
what should Vancouver do given this information that you have?
Well, in my mind, I mean, we have made progress. I can't answer your specific question about the chlorine plant, but there's this larger question about our infrastructure, and we have made some progress. I will give government some credit. They spent close to $4 billion on a program to retrofit and replace our schools. That's a big commitment to what I would call critical infrastructure. They've done seismic retrofits on all our bridges with one exception. They're going to replace the Dease Island Tunnel. I tell you, there's maybe some of you will feel the same way, but every time I approach the Dease Island Tunnel, earthquake, please not here. And because that is doomed in a strong earthquake. It's going to go down, I can tell you that. You don't have to be rocket scientists. But anyway, we've got critical infrastructure. There's public safety issues for sure, and our building codes are intended to protect people from injury, loss of life, and earthquakes. But we're not doing very well in terms of protecting our infrastructure. So if we get a big, strong earthquake, we're going to have, a lot of damage. And that's a big concern of mine because I've seen what's happened. I've been to Christchurch. I've seen what's happened in Christchurch. You go to Christchurch today, 3 years after that magnitude 6.3 earthquake, downtown is still cordoned off. It's been devastated by this earthquake. Not just in the short term, the 180 people who were killed, but the economy of that city. The city is depopulated. And it's my worst nightmare that Vancouver would experience something like that. So I have to say that we need to ensure that our critical infrastructure is better protected. I look at things like the Tsawwassen Ferry Terminal, very vulnerable. The Delta Port, they say it's earthquake resistant, but it sits right at the edge of the Fraser Delta on a bunch of mud. The Vancouver Airport sits on liquefiable soils. All those things need to be looked at a little more closely, knowing what we know about earthquakes. Because if we're hit by an earthquake and our economy goes down, we're going to lose that to Seattle or vice versa. And it's going to be a huge, huge mess for people for years and decades to come.
There's a
retrofitting you can do. It's very, very expensive. Very expensive, but that's sometimes what you have to do.
So there's a question here, yeah?
Yeah, thank you. Somewhat related question, two parts. The first part, what is the historic evidence for how much land level drop has happened in the Fraser Valley? Do you have anything on that? And then the second part is, I guess, along the related theme, we have under your floodplain bylaws.
Yeah.
Should we be thinking about a 5-year earthquake event? If we're losing, as you say, if the airport sinks by a meter,
Yeah.
we're in trouble. The dikes, then you're going back and building up dikes even higher with climate change and all these other
Yeah.
factors. It seems like we're in very vulnerable state.
Well, I have to say we are vulnerable to some extent. I mean, we live in a city, I wouldn't live anywhere else, but we live in a city that's got some exposure to flooding, sea level rise, earthquakes. I know I'm sounding like Dr. Doom again, but nonetheless, those are big issues, in my mind. The trouble is in convincing people to spend public funds to do something about it, because these are rare events. Even floods are fairly rare. And a lot of people think, well, we've got other priorities. And I would totally agree with that. Homelessness, lots of other issues. But in a sense, floods and earthquakes are inevitable. So what I think about the matter as a person, I may be willing to take a lot of risk, but I think the collective society should not be taking those risks. We want to ensure that our city is livable and that people are safe as a collective. It's kind of a different argument. I don't know if I answered your question, but we are vulnerable, and earthquakes can also cause liquefaction beneath dikes, so the two are kind of linked.
Would Vancouver drop?
Vancouver would not necessarily drop during this. We're too far inland, so we wouldn't experience that, but we'd experience the ground shaking.
All right. So there's a question here at the back. Yeah, and there's three actually at the back.
John, I want to thank you very much for the clarity of your talk tonight, the graphics and what you have to say, very, very valuable for us. I'm going back to one of the maps that you put up, which shows a kind of distribution of the sites and the energy levels of the quakes. And if I remember correctly, what you said is that Vancouver Island is divided, in fact, by a east-west running fault, contrary to the north-south, northwest, southeast.
Right. Maybe I'll just try and get that up real quick.
Yeah, if we could look at that. I have a question about that. Yeah, there it is.
This one?
Yes. But I couldn't, I could, if that's that division on the island. I have a question that is about the way in which Vancouver Island absorbs some of the strain and eventually in a quake would in fact absorb some of the energy, and then the way that that fault line might transmit some of the energy to the Georgia Strait. And that, have you modeled how, under certain conditions, the way that that fault moves would transmit energy into the Georgia Strait, and therefore?
And that's a very good question. And
So the question is it this break here, how does this affect the potential for earthquakes happening in different places and how the energy would be transmitted towards us, I guess?
Or maybe I mentioned, that line is essentially the northern boundary of the subducting plate. So the plate is moving down beneath southern Vancouver Island, beneath the Strait of Georgia. And north of here, you get kind of a very complicated tectonic environment. But that is what we call the north end of the Juan de Fuca plate. So that's the north end of the subducting plate. But I think if I understood your question correctly, it's how during one of those earthquakes, the energy that moves out from the source would kind of reverberate or move through the basin beneath the Strait of Georgia. Is that a fair question?
That's right.
But to be perfectly honest, I don't know. This is a very good topic for research. You can model, if you know enough about the subsurface geology, you can model what the seismic waves will do as it moves through that part of the crust. And we know that not just in these big earthquakes, but in smaller earthquakes, you get tremendous differences in the intensity of shaking, the ground motions, over small areas, and that's just geologically controlled. Some of it's due to the thickness of soft sediments, some of it's due to topography. During the Haiti earthquake, the most damage occurred on the ridges above the city. I think of that being at Simon Fraser. There's a lot of times when earthquakes will amplify shaking up on a ridge, and of course we live on a ridge at Simon Fraser, we have that issue there. And then you have the basin fill itself, the larger architecture of geology, not the just shallow subsurface. But during many earthquakes, you can get 3, 4, 5 times differences in ground shaking within an urban area. So in Metro Vancouver, we might get X amount of shaking in one place, or X amount of ground acceleration in one place, and 3X in another. And you can actually determine that if you know the subsurface geology and make some assumptions about the earthquake itself.
So there's a question at the back. That raises a question, but there's a question at the back, and there's one right in front of you. Just so this. Yep. So
yes, in terms of the environment, I'm wondering what your opinion is on sequestering CO2 underground, fracking, and pipelines, all which would be affected by volcanoes, I would think, and earthquakes.
So the question is, can you comment on using the earth to do things like storing CO2? And then there was, sorry? And fracking. So some of the things that we do now under the earth, and how are they affected by what you know about earthquakes?
Well, there are instances where hydraulic fracturing has induced earthquakes. That's well documented up in the Horn River area in northeastern BC. They're not large earthquakes, they're small earthquakes. I know that there's a really very important study now being done in the foothills of Alberta because they're fracking extensively in the foothills area. And there are some very important reservoirs, dams in the area, and even small earthquakes could induce damage to those structures, and they're fracking within kilometers of some of these facilities. So there's a very active research program going on to try and determine, what the possible magnitude of an earthquake might be. Not all fracking operations produce earthquakes, but we've noticed that in the eastern foothills of the Rockies that's rather common. And it's probably due to the fact that those rocks are still under tectonic stresses. And so they're kind of hairline in a sense. It doesn't take much to actually set off earthquakes. They've all been small. We haven't had a fracking-induced earthquake greater than about magnitude 4. So they've all been small today.
Yep.
Okay, I was wondering about the correlation between like the supermoon pulling effect and the solar gravitational pull, and the correlation of what the man said behind me about the depletion of the liquid weight of the fossil fuel. Are we being pulled as the astral projected path, which has changed obviously from our planet becoming lighter? Is that correlating also with the earthquakes? Because we're getting pulled closer to the sun, and we're also getting pulled closer to the moon on different parts?
So is there any large-scale patterns in earthquakes through history because of the way that the Earth and the Moon and the Sun are sort of interacting with each other?
So gravitational forces exerted by the sun and the moon and the tides. You know, I have a colleague at SFU who believes that's the case as a trigger. It's not a cause, but it can maybe be a trigger for an earthquake that's going to occur anyway. That's very controversial, but there are definitely scientists who think there is a link there. My comment is that, you know, that's only could operate as a trigger. It can't be a cause. So you need tectonic stresses to really produce earthquakes. But if you bring it to the threshold of the earthquake occurring, that maybe something like that could actually trigger it. Those gravitational forces are certainly important, you know. I mean, that's what controls the tide, so they're not trivial by any means.
There was I think here, yeah.
Given what you said about the potential for the amplification on structures, for example, like Burnaby Mountain on the North Slope, do you think it's a great idea to triple the capacity of tank farms to 5.5 billion barrels? Would you suggest that's a good business model?
Sorry. So just, I didn't quite catch. So given what you know about how earthquakes might happen and what might happen with earthquakes here in Vancouver, is it a good idea, sorry, for what?
To expand.
The tank farm on Burnaby Mountain. Sorry, that's
the Kinder Morgan.
Okay, so the Kinder Morgan has a tank farm on Burnaby Mountain. Is that a good idea?
It's kind of a loaded question, but how can I say, yes, it's a great idea? Actually,
what should they be worried about?
I'll kind of answer that by saying, you know, that's a public debate that should take place. You should be asking Kinder Morgan, I suspect they have, but you should ask them if they've taken into account, you know, the seismic stability of the ground that they built those facilities on.
There's little risk, and I'm asking you, as a geologist, do you think that's a sound conclusion based on what you know about earthquakes and the potential for?
I don't, to be perfectly honest, I'm not trying to dodge the question. I'm a straight shooter, but I don't know what sort of provisions they have for those facilities. I don't know. You know, it's not something I've been engaged in with, not involved with Kinder Morgan. So
there's
I don't know.
The woman
if I
has,
knew,
okay,
I'd try to answer.
So there's a question here right at the back.
Yes, thank you. I had accepted that the lowlands where I live were likely to flood, but then you really got me when you said that the ridges will shake harder. But my question actually goes to the fascinating discovery that the marshes had dropped, and you could use that as the trace for showing where these very large magnitude 9 earthquakes had occurred. My question is, why didn't liquefaction of those very soft soils mask that evidence?
Okay.
So the question is that the evidence is that the marsh dropped, right? That's how we found. That's how you've all found out that they're earthquakes. But if the earthquake was so big, why didn't the whole thing just liquefy and just erase all that evidence?
Well, that's a very good question, and it's very, you know, you really thought that through. And we do get liquefaction during these earthquakes, and typically it's localized. It's not just everything liquefies. Like when we get a big earthquake, Richmond isn't just going to slide into the sea. What happens is you get the subsurface soils at depths of probably 3 to maybe 15 meters can undergo liquefaction locally, and that causes irregular subsidence of the ground. It does cause irregular subsidence. It causes cracking, so you get these sand volcanoes that we saw in Christchurch. But it's not like the whole area uniformly drops 1 to 2 meters. It's very irregular. It's totally, in terms of earthquake damage, liquefaction damage is one of the most, important factors in looking. And Richmond is ground zero for liquefaction in a strong earthquake.
So just as a follow-up, when you say it liquefies, does that mean if you were standing there, it would become muddy underneath you, or is it deeper in the soil that you wouldn't see?
It's a little deeper in the soil. It
it
usually occurs below the water table because the soils have to be saturated and they have to be granular. You can't have sticky clays, they don't liquefy, but sort of sandy sediments are what liquefy, but they have to be water saturated. So it typically occurs below the surface, and it can be fairly shallow, but it can actually go down to about 15 meters. So if that were to happen, you wouldn't sink up to your waist in mud, but you would kind of experience sand getting vented out onto the surface and cracking of the ground and damage to sort of subsurface infrastructure like gas lines, water lines, they all go.
And stuff that we saw in the video there.
Yeah.
I'm just curious, if the magnitude 9 earthquake was to happen, how would that affect the volcanoes in this West Coast area, or if it would affect them at all?
Right, so here's another connection. So is there a correlation between earthquakes in different parts of the world? Is there a correlation between earthquakes and volcanoes around here, or in the same place?
Well, that's a good question too, and not normally, when a subduction zone earthquake occurs. When the big one in Alaska occurred, I don't think there was any volcanic activity, but the two phenomena are related. They're both caused by subduction. I think in the case of the Sumatra earthquake, there was a temporal link between a volcanic eruption and that big earthquake. So I think it can occur. It's just normally the plumbing system for the volcanoes is a bit detached from the actual fault plane. So it wouldn't be common, but I wouldn't say it couldn't occur.
Yes.
How do they determine lock zones? What is the technique?
Sorry, so how did they determine locked zone? Oh, how did they actually determine the locked zone? So you said that this was a very, very important piece of the puzzle. How do you actually figure that out?
It's based partly on the surface deformation. So if you think about it, if you can map out what's getting squeezed and what's getting uplifted, you can kind of project that down to the fault in the subsurface. The deformation pattern on the surface constrains where that zone is. And then you have to also make some assumptions about the temperature at the fault interface, because if the temperatures exceed about 300 degrees, the rocks can't actually, they're not brittle enough to actually store the strain. So as you go deeper along that fault, it gets hotter and hotter and hotter, and you reach a kind of a threshold beyond which the rocks are no longer storing strain. So it's partly temperature controlled. At shallow depths near where the fault intersects the ocean floor, the temperatures are low, and so the rocks behave brittly and they can actually store strain. But when you go deeper and deeper, the temperatures increase and you reach a threshold temperature beyond which they just slip. They actually do slip without storing any strain. And so you end up with this kind of band of where the two plates are hung up against each other. But it is fundamentally the pattern of how the surface of the ground is deforming that kind of tells you what the width of that band is.
And we'll go on to, and just to remind us, the subduction plate that's going down is about 60 kilometers below us. Where is it? Right here?
I should have checked that because I knew
Roughly.
you were going to ask that. But I think it's 50 or 60.
Okay, so it's 50 or 60 kilometers.
That's not far, if you think about it.
That's from here to Chilliwack, no?
From here to Chilliwack, you go down. If you could drill down, you'd be at that big mega fault. I like to think that. But it would be hotter than the hinges down there.
So there was a question here, yeah? Yeah.
Yeah, just wondering, this map shows a striking lack of tectonic activity below Seattle.
Down here?
I guess there's a line there.
It's a fault boundary. It's called the Canadian
Yeah, but there's some
U.S.
California earthquakes that I've heard about that happen.
Yeah, so what happens down here? What's going on down here?
We all should be moving down there, I think.
There was one slide that you showed that had a periodicity of big red blotch earthquakes along the southern part of.
Yeah.
That said that
that's a
there were
good question.
250-year increments, and on the north side of the big
This one.
red blob, there was 500-year increments. Could you talk to that a little bit?
Yeah, so this kind of, this plot on the left with the 530-year return interval is based on full-length ruptures. It's the ones that you can infer have occurred along the entire length of the subduction zone.
So, is this one, the Fuca subduction
one on the
zone? This is
left,
just the local one, right?
Yeah, and so those numbers, the people who did the work just numbered them 1 to 20. And so there are these, like I said, these large number of full-length ruptures, which I find a little curious. And when you get down here to the south end, there's some additional ones that increase or decrease the recurrence interval. So earthquakes, big earthquakes are more frequent. And they think that's due to the fact that this is where the San Andreas Fault comes out to sea, and you get the additional complication of earthquakes triggered by movement along the San Andreas Fault like in 1906. So that's a kind of a messy area. This is the southern end of the Juan de Fuca Plate, and this is where the San Andreas Fault, just north of San Francisco, goes offshore at Cape Mendocino. So I know I'm a little wordy, but the point is that at the southern end of the subduction zone, you get the additional strains generated by the right lateral strike slip along the San Andreas Fault. I still think it's peculiar. I just kind of can't buy into having full-length ruptures, 1,100 kilometers every earthquake that affects us. I think they have to be segmented, but that's just my bias.
Can we go here, and then we'll go back to this one? Yes.
You think there'd be different degrees of lockedness, and that the longer the time period goes, that there would be more pressure that would build up that would lead to a bigger earthquake.
Yeah.
But the chart that you had with time on the x-axis and the size of earthquake on the y-axis didn't seem to show that.
Yeah, that's a very good observation.
So so the question is, are earthquakes bigger? Are earthquakes bigger if you wait longer between them?
Yeah.
And the evidence doesn't support that. This one, yeah. So why is that?
It's a good one. Well, there is a little bit of a relationship. I wouldn't claim it's very good. You get sort of big earthquake. Well, no, it's not very good. I take it back. I don't know. Kind of this, I should say that this is a bit of a weak proxy, and I haven't explained how they actually determine the magnitudes of those events. I think they're well dated, and I think they're real, but the proxy for the magnitude, it's based on what we call turbidites in the deep sea, thicknesses of the layers, how widespread they are. I don't think it's a very good proxy for earthquake magnitude. So I'm skeptical. I guess I'm a skeptic in many ways, but I'm not so sure that those are necessarily good indicators of earthquake magnitude. But I haven't really explained how that database, I just didn't have time. It's an interesting story in its own right.
There's a question here. This will be a second round. So if there's anybody else? Okay, sure, go ahead. Yeah.
You talked about the biggest risk being from transformed, like magnitude 6 or 7 quakes. Now, I understand there's also some transformed faults running through the area of the lower mainland and northwestern
Yep.
Washington. How well have those been mapped out?
So we've been talking about subduction quakes, these big ones, and you said the smaller quakes, which are the ones where they slip this way.
Yeah.
May be more important. So how much do we know about those fault lines here?
Those are crustal faults. I wouldn't call them transform faults. Transform faults are plate boundary faults, but they're nonetheless, sorry, Jared. He's defending his thesis in a few weeks, and he's my student, so I've got to continually correct him all the time. Just kidding. He's a bright guy. He asks good questions. That was a good question. These are crustal faults, and they are storing strain too, and they're a bit decoupled from the actual megafault that extends down below the surface. So it's, I haven't talked about the crustal faults, but they're the ones that do generate the magnitude 6 and 7.5, and they're well mapped out in Washington and not so well mapped out in southern BC. But Seattle, gosh, there's a big one that goes right underneath Seattle that produced a monster earthquake 900 years ago. Seattle's got a big problem. There's also a series of them that extend north of, that have been mapped out north of Vancouver, right up to the border, right up to Bellingham. There's one in Bellingham. There's one south of Nooksack, but we don't allow them in British Columbia, so there's none known in British Columbia.
So there's more work to be done
I'm
there.
being facetious. I think they're here too. It's just they haven't been documented yet.
Are there any? Yes, Rolf.
John, someone asked earlier whether we had any local evidence of subsidence.
Yeah.
And I think we do have some
We
local
do.
evidence of subsidence.
Yeah.
And could you give us some magnitude? How much drop have we actually measured? Let's
Yeah.
touch in Boundary Bay, for example.
So wait, this is during an earthquake?
Yeah.
Or just generally?
No, paleo earthquake.
Paleo earthquakes, yes. So
Yeah.
evidence for the land going down in Boundary Bay and paleo earthquakes.
Now, Rolf and I did a study in wetlands south of Vancouver in the Serpentine Nickel River area, and we found evidence of paleo earthquake land level drop, probably modest, not 2 meters, something of the order of tens of centimeters, and likely not related to a plate boundary earthquake, but rather a local earthquake of some sort. As I remember, it's been a long time, Rolf, but I remember it was kind of about 1,700 years ago, something like that. Yeah. And interestingly, there's evidence for liquefaction at that time. On Annacis Island, when they were upgrading the sewerage facilities there, they made an excavation, and there were all sorts of sand volcanoes and sand dikes. And if you fly into Vancouver, look down on Annacis Island, you'll see every Korean and Japanese car parked on Annacis Island, waiting for the next earthquake.
Yes, sir.
John, you've got that graph up there, and let's pretend for the moment that it's real. And
That's
the size of those large magnitude earthquakes is tapering off through time. The largest one ends each cluster.
Yeah.
Let's go back in time a little bit, just a tiny bit more, to the last glaciation.
Mm-hmm.
And you've had a major change in mass balance, such that prior to, say 10,000, 11,000 years ago, you had an ice mass on top of the northern part of North America,
Yeah.
depressing the land, of course, but that mass was greater on the North American plate. That was shifted over because now you've got a greater mass of water on top of the oceanic plate. You've got 130 meters more of a water column on top of the oceanic plate. Is anybody modeling that change in mass balance and wondering what its effect would be on the incidence of things like this?
Nobody's done that. That's.
Do you want to repeat? that?
Oh, yeah.
Do you want to sort of paraphrase that?
It's a very good point. It appears, if this is real, that there might be a trend towards smaller events with time. And the comment was, well, just before this, you had a radically different configuration of glaciers in British Columbia and all through Canada. You had big ice sheets over British Columbia and Canada. That would definitely perturb the crust. We know that those ice sheets depress the crust probably at least 500 meters, so a lot of land level lowering just due to the weight of the ice. Then at the end of that glaciation, when these ice sheets retreated, the land rebounded like a cork. And that imposes, I think might get your point, is it imposes stresses, and also the water that was formerly locked up in the ice sheets then goes back to the ocean. So the continental shelves get loaded with water, that can actually have an effect. So you're really changing the whole potential field, or the whole gravitational field in this area. And I think, long-winded, longer than the question, it could have an impact on the size of, and frequency maybe, of earthquakes closer to that time 10,000 years ago. The answer is very short. No one's looked at it, and it would be probably interesting to do that.
Do you have any other questions, comments, general concerns about the future? Yes?
Don't leave Vancouver. It's a great place to live.
Actually, about the 14-month period where there's the slip reversal and kind of.
Oh yeah.
What's the latest information on that? Is that increase in risk, a lower risk?
Okay, so did you mention a 14th month slippage reversal?
That's a good question, because our fantastic geophysicists at PGC have detected what they call ETS events, episodic tremor phases. And about every 12 to 14 months, we get kind of large numbers of micro-earthquakes. They're funny earthquakes, and they're small. But it's like you light up the whole area close to the subduction zone with earthquakes. And at the same time, you get surface deformation related to those events. And the events last about a week, 10 days. And the notion is it's kind of, as the plate is going down, it's stuck, but you get a little bit of back ratcheting. Think of a ratchet, and it goes down, and then boop, a little bit of slip, zip, and it manifests itself in hundreds of tiny little earthquakes and a little bit of land level change. And so the last I heard, and they may have more up-to-date ideas about this, but that would increase the likelihood that you're going to get one of these big earthquakes in that 1 week period. The probabilities go way up. It's like, could be the straw that breaks the camel's back. You go like that, and then back ratchet, but poof, off it goes, during one of those 1 week periods. I don't know where we are in that cycle now, actually. Usually.
What month does that occur? Sir.
Okay, so the first question is a little bit facetious, but it goes to the second part. Should I pay for earthquake insurance?
Oh, my God.
Okay, but the real question is, with all the damage happening in Christchurch and the lack of the city to rebuild itself right now, complications with insurance and permits.
Oh, yeah. It's a mess.
Yeah.
Sorry, so should we have earthquake insurance, if there is such a thing?
There is.
And so the second question was?
Well, how has Christchurch been able to rebuild itself with the difficulties of getting your payment from your insurance to rebuild your buildings, get your permits through the city?
Yeah.
Okay.
It was taking a long time.
It's a mess.
So so can you tell us a little bit more than, besides that it's a mess?
I don't know the full details, but in Christchurch they have an earthquake commission. It operates a little differently. In theory, the New Zealand government is covering the liability that homeowners are exposed to, but they're broke. It's $30 billion, a country of 4 million people. They don't have the money. So I don't know how that's played out. As far as earthquake insurance, I used to have it, not anymore, for two reasons. One is the deductible has gotten crazy, and it's gotten more expensive. And if I look rationally at the most likely scenario, it's going to have a slightly damaged. You're not going to have one of these catastrophic earthquakes. It's going to be a earthquake, 70 kilometers away that causes some cracking and structural damage. You're going to pay the whole bill anyway. I know that's just my personal point of view. And in the back of your mind, there's always, okay, in a catastrophic event, good old Mother Canada will step in and bail you out. Whether that happens or not, I don't know. But it just got too expensive, and the deductibles were crazy. I'd have to pay for half the damage, and it didn't seem like a good thing to do. But I think you raise a good point, is that when you have this very long period of recovery, it takes forever to actually compensate people for damage. And somebody, Paul, you may know more about.
Just one comment or question, because I know some people have moved down Wellington and that part. Christchurch, first of all, the earthquake was only 5K down.
Yeah.
One of the reasons it did so much damage to a little earthquake. I used to tell students, two things you look at an earthquake, one's magnitude, two's depth.
Yeah.
That determines it. In Christchurch, apparently, they have zoned, your house was green, orange, or red.
Yeah.
Red meant you weren't getting it back. Orange meant maybe, and they moved those over time.
Yeah.
So people whose houses were orange, and one of my friends' friends had that same thing happen. His house was orange, and came home one day, and no, you're not living like this. Christchurch is built on the city centers on deltaic soil. So I didn't realize things about deltaic, but it is a sort of the equivalent of Richmond. So they've done that, and it basically destroyed the whole of downtown.
Yeah.
So it'd be more like the whole of number 3 road being destroyed rather than where we are now, which is solid rock. So they
Yeah.
went out, great areas. It was a huge area, as John said, very relatively few people.
Yeah.
And relatively little money, but it was because it was on so shallow, on
Yeah.
deltaic soil.
Absolutely.
They sort of done like they did the Calgary floods. They say, you can build here, but we're not insuring you. We're not going to rebuild there.
So where you build is very important. That's
Yeah,
the thing.
and that Christchurch earthquake was, I mean, magnitude-wise, it wasn't big, but it was a very worst-case scenario. As Paul said, you know, shallow earthquake, I think the epicenter was about 7 kilometers from the city center, really close in. And also the energy was directed right into the city. The way the fault slipped, it sent the energy at supersonic speeds right into the city. They got ground accelerations. We measure ground accelerations relative to the gravitational constant. So 1G, you know, if you'd be suspended in air momentarily, and they were having ground accelerations for 10 seconds in excess of 1G. Nobody thought that could happen in a magnitude 6 earthquake. In other words, things were suspended in air for momentarily. You can imagine what that does to a structure that's being torqued by those. But that's a worst case scenario. As I say, the most likely scenario is we will experience an earthquake. It will be, you know, a mildly damaging one, and we'll pay the deductible, I think, for an earthquake like that.
We'll carry on.
That's my personal bias. Now, I've discouraged people from taking out an earthquake.
Well, I think that's maybe worst case scenario in Christchurch, maybe not worst case scenario in Vancouver. Maybe that's a good place to stop. Please join me in thanking Professor Clague once again.